Good morning, class. We are looking at statistics practice test number 5. Module 5 covering chapters 10, 11, and 12. Chapter 11, goodness of fit and contingency tables. Goodness of fit test in multinomial experiments. We're going to go over that through some examples. Here are the observed frequencies from 4 categories: 5, 6, 8, and 13. At 0.05 significance level, test the claim that the 4 categories are all equally likely. This is the test of hypothesis. State the null and alternative hypothesis. What is the expected frequency for each of the 4 categories? What is the value of the test statistic? Find the critical value, make a decision. This part is different because of the goodness of it, but the other 4 is familiar. And so what are we dealing with here? Number 1, let's give the definition. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. Goodness of fit hypothesis tests are always right-tailed. If the sum of this weighted square deviation, chi-squared, is summation of O minus E quantity squared over E. O stands for observed, E stands for expected. What we have observed and what is expected. We're going to discuss the expectation in a moment. Is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, the chi-square goodness of fit test is always a right-tail test. Now, when it tests the claim that 4 categories are all equally likely. That means we use E, the expected value is N over K. N means the sum, the total sum. K means the number of categories, which is 4. Otherwise, you write is N times the proportion, because if they have different proportions for each observation, then you can calculate it in that fashion. Having said that, E equals N over K. N is the summation of observed values, 5 plus 6 plus 8 plus 13. K is the number of categories. And we get 8. So that is the expected value. On a normal basis, that's what we expect, but this is what we have observed. Given it's a multinomial experiment because K is 4 categories. Remember, in the case of a binomial, there are 2 categories. In short, there are more than 2 categories. It becomes a multinomial. So it's more than 2. It's 4 categories. So multinomial. Alpha is given as 0.05. We use a goodness of fit test because of the number of categories is more than 2. Each expected frequency has been calculated to be 8, and thus satisfy the requirement of being a value of at least 5. When it comes to multinomial experiment, this number must be at least 5. If expected count is less than 5, the result of chi-square test will not be accurate. It won't work because the assumption that it works with the chi-square distribution, it fails. And the assumption is must be at least 5. And in this case, it's 8, and it's good. So we're going to continue. All right. So we have already discussed the goodness of fit test. We have the formula for test statistic chi-squared is summation of observed value minus expected value quantity squared over E. Degrees of freedom is K minus 1. K represents the number of categories. And E is N over K, summation of O over K, which is 8. We already have all of those, okay? Now, and this is a chi-square distribution table that is going to be used. It's a portion of it as far as, space permits. So step one, H0, P1 equals P2 equals P3 equals P4. I hope you remember in the binomial for 2, we would have 2 of them. Now we have more. In this case, how many categories? There are 4 categories. So we go with that. Now, and that is the claim because we are looking at whether they are equally likely or not. So that would be the claim. H1, at least one of the probabilities or proportions, at least one of them is different from the others. That makes it right tail test because they're equal, right? If one of them is different, that makes it H1, the alternative hypothesis, and it's a right tail test. So here's the formula, and we are dealing with a small size, only 4. So I'm going to show you how it's done by hand, of course. The observed value minus the expected quantity squared over E. So this one would be 5 minus 8 quantity squared. This would be 6 minus 8 quantity squared, 8 minus 8 quantity squared, 13 minus 8 quantity squared. Add them up, divide by 8. So instead of dividing each one by 8, you can divide the sum by 8. You get 38 over 8 or 4.750. That's test statistic. That's the formula for TS, test statistic. Critical value comes from the choice of alpha, degrees of freedom n minus 1 or 3. Okay. So we have degrees of freedom of 3 on the left column. Look for the degrees of freedom, which is 3, and the area is 0.05, which gives us the number 7.815. Now, this is the test statistic. This is the critical value. Let's put it into a graph. Here's the graph of a chi-squared, which is skewed to the right. Here's alpha of 0.05. Here's the critical value of 7.815, and our test statistic is way into the non-rejection region. Again, doesn't have to be to scale. It's just way into the non-rejection region, not the tail. Therefore, don't reject H0 or fail to reject H0. Then we go back to what we wrote. So if we are not rejecting H0, we are not rejecting the claim is true. Now we are going to reinstate what we just have come up with. Remember, all calculation is about part A only, and then it's our doing. There is sufficient evidence to support the claim that the 4 categories are all equally likely. Okay. Now, by any chance, and in some cases, they might take it to be a two-tailed test, because as far as the wording is concerned, if we go back to the wording, okay, at 0.05 significance level, test the claim that the 4 categories are all equally likely, then the alternative hypothesis would be not equal, and one may take it as a two-tailed test. Even if you take it as a two-tailed test, degrees of freedom remains the same. Alpha, you cut it in 2, becomes 0.025 on the right and 0.025 here. And if you look those up, okay, you get 2 values, okay, this one and this one, where 4.75 is between the 2 values that I have here in between 0.216 and 9.348, just to give you an idea. It works that way in case. Now, of course, you can go with a technology, as I've mentioned, online or TI calculator. So what we are going to do, we are going to use a couple of lists, and we're going to clear L1 and L2, and we're going to do stat test chi-squared GOF, goodness of it, GOF test. We're going to enter L1 and N2, and degrees of freedom is n minus 1, calculate. So we put into L1 5, 6, 8, 13. Always you put the observed value in L1. In L2 is the expected value. Each one is expected to have a value of 8. So L2 would be just 8, 8, 8, 8. And now chi-squared goodness of fit test, the observed has L1, the expected has the L2 list. Degrees of freedom is n minus 1, 4 minus 1 is 3. You calculate. This is what you get. So what do we get here, everybody? Number one, this 4.750, which was a test statistic, is calculated for us. Number two, the p-value, everybody, is area to the right of test statistic. So here's the p-value, clearly 0.1910, way larger than alpha of 0.05. P-value of 0.191 larger than alpha of 0.05, and you have the same result. Don't reject H0 or fail to reject H0. Very straightforward, everybody. Here's another example, goodness of fit test in multinomial experiments. A professor asked 40 of his students to identify the tire they would select as a flat tire of a car carrying 4 students who missed at least an excuse. Who missed the test. It's an excuse. The following table summarizes the result. Use a 0.05 significance level to test a claim that all 4 tires have equal proportions of being claimed as flat. Because if that's the case, it's hard to, for everybody to have the same answer. Okay, because to have the same answer, all 4 students, 1 out of 4 to the power of 4. So in any event, here's the tire. Left front, we're going to go capital L, capital F. Those who said left front is 11. Right front, lowercase r, F15. Left rear, capital L, capital R, 8. Right rear, lowercase r, capital case R, 6. So left, right, front. Okay, left, right, rear, front. So E is n over k summation of over k 40 over 4 or np. 40 times 1/4 or 0.25 is 10, either way. So there are 40 students divided by 4, it's 10. So that is the expected value. There are 4 tires. So each one has an expectation of 10. That would be the expectation. Each expected frequency, 10, does satisfy the requirement of being a value of at least 5. Step 1, H0. Probability of all of those, for example, LF, left front, and the rest of them are identical, and more specifically, they are equal to 0.25 or 1/4. And that is the claim. H1, at least one of them is different. At least one of the proportion is not equal to 0.25. So P sub I is not equal to 0.25. It appears to be a two-tailed test, but remember, with chi-squared, we go with the right tail test, okay? And so having said that, now we're going to calculate the test statistic. Again, it's a small data. We can do it by hand as follows. 11 minus 10 squared plus 15 minus 10 squared plus 8 minus 10 squared plus 6 minus 10 squared, and the entire thing divided by 10, and we get divided by E, 10, and we get 4.6. 46 divided by 10 is 4.6. So if we evaluate the test statistic, chi-squared is summation of O minus E observed value minus the expected value quantity is good over the expected value. It's the same as the previous one. Critical value alpha is 0.05. Degrees of freedom is K minus 1 or 3. And so chi-squared is the same thing. We picked it up from the previous page, 7.815. Again, we are going to do the drawing. As you can see, this is chi-squared skewed to the right. This is the location of a critical value. Test statistic is somewhere here, way into the non-rejection region. Therefore, the decision is fail to reject H0 or don't reject H0. Now we go back. If you're not rejecting H0, that means the claim becomes true. So the claim is true. And now we are going to elaborate, which means there is sufficient evidence to support the claim that all 4 tires have equal proportions of being claimed as flat. So they all have an equal chance. They all have an equal chance of 1/4 or 0.25. That's the idea. Okay. And so again, if we go with the two-tailed test, and again, we don't, the numbers are as we picked in the previous one. 4.6, as you can see, is in between. You have to do the drawing. You put it here, and it's in between, and it's in the non-rejection region. So what does it mean when 4 students identify the flat tire? It is not likely for all to select the same tire. That's the idea, because it's hard to do so. Now let's discuss contingency table and what comes with it. A contingency table or two-way frequency table is a table consisting of frequency counts of categorical data corresponding to 2 different variables. One variable is used to categorize rows, and a second variable is used to categorize columns. When data can be tabulated in table form in terms of frequencies, several types of hypotheses can be tested by using the chi-square test, such as the test of independence of variables and the test of homogeneity of proportions. And while they use similar methods, they serve different purposes. The test of independence evaluates whether 2 categorical variables in a single sample are statistically independent. It tests the null hypothesis that there is no association between the row and column variables in a contingency table. That is, there is no dependency between the row and the column variables. In the test of independence, observational units are collected at random from a population, and 2 categorical variables are observed for each unit. The purpose is to determine if 2 variables are related within one population. Data structure is 1 sample, 2 categorical variables. Example, gender and voting preferences. Question, it answers. Is there a relationship / association? Relationship, association mean the same thing here. Between variable A and variable B in one population. Example, is there an association between gender and preferred type of exercise? So that's contingency table and the test of independence. Now, what about chi-square test of homogeneity? They are very similar class. Test of homogeneity of proportions is also called, is a test of the claim that different populations or groups have the same proportions or distributions of a single categorical variable. The test of homogeneity of proportions is used to determine whether the proportion for a variable are equal when several samples are selected from different populations. It tests if the proportions of categories are the same across different groups. So test of homogeneity, the purpose is to compare the distribution of a categorical variable across two or more populations. The question it answers, are the proportions of a categorical variables the same across different groups? Data structure, multiple samples, one variable, for example, preference across age groups. Example, do 3 age groups differ in their preference for a political candidate? Both tests use the chi-square test and are computed similarly using a contingency table, but their designs and hypotheses differ. So some of the things that might help feature used for sample structure, goal, typical wording of null hypothesis. For the test of independence, it is used for relationship between two variables, but test of homogeneity, comparing groups on one variable. Sample structure, one sample, two variables. This one, multiple sample groups with one variable. Goal, test of association or dependency. Goal, test of equal proportions. Typical wording, variables are independent. In this case, proportions are equal across groups. Test of independence and test of homogeneity are always right tail. And if the sum of these weighted square deviations, summation of O minus E quantities over E, is small, the observed frequencies are close to the expected frequencies, and there would be no reason to reject the claim that it came from the distribution, from that distribution. Only when the sum is large is the reason to question the distribution. Therefore, test of homogeneity is always right tail test. Here's an example of a test of independence. Using a 0.05 significance level, test a claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or a girl. And here's the table that we have from the Titanic: men, women, boys, girls. Those who survived, we have 332 men, 318 women, 29 boys, 27 girls, and those who died, 1,360 men, 104 women, 35 boys, 18 girls. So that's the given table. And so what do we do here? The expected frequency for each cell is the row sum times the column sum over the grand total. So you're going to add this to, this is the total, add this to, add this to, add this to. You're going to add this row, you're going to add this row. Over here, that would be the grand total. So this one, then you add the columns. Now this one, you, so again, for example, 332 and 1360 is 1690 to add the depth. Now let's add this way and put it here. That's the sum of the rows. This number, when you add these 4 numbers or these 2 numbers must be the same. This is the grand total. Okay. Everyone. So that is important to understand. Now, use the formula to find expected frequencies for the upper left-hand cell. So what we are going to do, we are going to use this formula for this one by hand, and then we repeat it for everyone. For example, for 332, the process is what? the expected value. So the observed value is 332. The expected value is the row sum, row sum 706 times the column sum 1692 divided by grand total 2223. So those are the three values. 706 times 1692 divided by 2223. And the answer is 537.360. Again, granted, this is supposed to be a discrete value. You can approximate it if it need be, but we're going to keep it as that for the sake of our calculations. Okay, so if we continue using the same procedure, the table of expected values becomes. So for 332, the expected value was calculated. If I wanted, for example, for this number, then I multiply this one by this one divided by this one. For this number, multiply these two numbers divided by that. This one, multiply this number by 15, 17, if I want it for 18, divided by that. So we get the following table. Again, I showed the calculation for one, we can figure out the rest. So what does it mean? The interpretation is very important, everybody. Interpretation. To interpret this result for the upper left-hand cell, although O is 332, we observed 332 men survived. We would have expected this many, 537.36 men, to survive if survivability is independent of whether the person is a man, woman, boy, or a girl. That's very important to understand the meaning of that. We would have this many survive if there was an independency. There is a discrepancy between the observed value of 332 and the expected value of 537.36, and such discrepancies are key components of the test statistic that is the collective measure of the overall disagreement between the observed frequencies and the frequencies expected with independence between the row and column variables. So that's the meaning of it. To interpret this result for the lower left-hand cell, we can say that although O is 1,360, so this one, men actually died. So this many died, okay? But the expectation would have been, okay, actually died. We would have expected E to be this number, 1,154.64 men to die, if survivability is independent of whether the person is a man, woman, boy, or a girl. So in short, these are the values that did occur. These are the values that would have occurred if the expected value, if there was a independency. So that's the concept. And note, summation of E in row and columns are consistent. Example, column 1, this number and this number. In other words, if you add up the expected values, you should get the sum. This number and this number, they add up to 1692. This number and this number, they add up to 422. Or this number plus this number plus this number plus this number must be 706. I mean, they may be a tad off by the round of error, but they're almost identical. So for example, again, these two numbers, they do add up to 1692. That's another way to check that we haven't made a mistake with our calculations. All right, so first the requirements. Let's assume random selection. And number 2, results are frequency counts, and E is larger than 5. E is way larger than 5 for each case, so we don't have to worry about it. So how do we write the first step, H0 and H1? H0. Whether a person survived is independent of whether the person is a man, woman, boy, or a girl. The row variable is independent of the column variable, and that's the claim. Again, there are two ways to write it. a general case for anything, whether in this example or another one, you can write the row variable is independent of the column variable. That basically says it all. But what does it mean? It's the previous statement. And so H1, surviving the Titanic and being a man, woman, boy, or girl is dependent. The row variable is dependent or related to the column variable, and that's a right tail test. Remember of the limitation of chi-squared, we make it a right tail test, and we are going to use this formula to calculate the test statistic. By the way, degrees of freedom is r minus 1 times c minus 1, and for the sake of argument, so just to discuss that, understand that we have 1 and 2 rows, we have 1 and 2 and 3 and 4 columns. So 2 minus 1, 4 minus 1. That's how we get it. And of course, alpha was given as 0.05. But using this formula, everybody, using this formula. Look at the very first cell, 332 minus 537.36, quantity squared, and divide by 537.36. You do the same thing for each and every one of them, all the way to the last one, which is plus 18 minus 30.709 quantity squared over 30.709. So we can see how it's calculated. I will discuss the calculator and everything in a moment, and you put it into calculator, it gives you 507.084. So that's the test statistic, and you can tell right away it's huge. Okay. Degrees of freedom is, as I mentioned, 2 minus 1, 4 minus 1 is 3, alpha is 0.05. Again, 2 because we have 2 rows, 4 because we have 4 columns. Okay. Or the number of rows minus 1, C, the number of columns minus 1. Their product is 1 times 3 or 3. And from the table, we get chi-squared of 7.815. And obviously, if you do the drawing, this is way larger than the critical value. It's way into the rejection region, and obviously you are going to reject H0. So if you're rejecting H0, you're rejecting the claim. And so you do the writing as follows. There's not sufficient evidence to support the claim that when the Titanic sank, whether someone survived or died is independent of whether that person is a man, woman, boy, or girl. Or in short, survival and gender are dependent. That's another way of writing exactly the same thing. Now, and by the way, as far as the p-value is concerned, the area to the right of this number, which is practically 0. But in any event, what about a technology, for example, TI calculator? Okay, we are going to put the information we have, the observed value, into one of the matrices because it's in the matrix format of 2 by 4. Okay, so access matrix, second, and press x to the power of -1, edit, enter dimension. So here's what you do. Matrix A, dimensions 2 by 4, and you put 332, 318, 29. There's no more room to show you, and the rest of them, the bottom one is 1360, 104, and so forth. So you write those. Okay. Now, stat tests, chi-square test. Okay. So we get that one. The observed is A, the expected is B. Don't change that. We're going to keep, because we put this into A, we keep it as such. What is the expected value B? We didn't say anything about that. It will automatically calculate the expected value matrix and puts it into the B matrix. Okay. So what did we get here? Okay. First and foremost, look at the value of chi-squared. Look at the value of chi-squared we calculate. So it calculates the test statistic for us. Why is it different? Because notice when we wrote the expected value, we used a couple of decimals or more or less. They have used a lot more. Okay. So you know how they came up with that. Okay, that's important to understand. Okay. So clearly they have more decimals and a more precise answer. The next thing is look at the p-value, 0, which means the p-value from the chi-squared table. Chi-squared is 5, or remember this one, the area to the right of this number, the highest value is 12.838 in the table. The p-value is less than 0.05. That's how the table shows you. Technology gives you 0. Now, also, I put this one. This is the expected frequency matrix. Look at the numbers, 537.36, and the rest of them, look at the bottom, 1154.64, see 1154.6396, and it uses a lot of decimals, and the rest of them, there was no more room. My point being, when you do this by technology, and over here, the observed value is A, the expected value B is generated for you automatically if you look up the B matrix. Test of homogeneity using the following table with a 0.05 significance level. Test the effect of pollster gender on survey response by men. Look at first the table, everybody. Men who agree, men who disagree, men, women. So this is the gender of the interviewer. When it's men who agree is 560, men who disagree 240. For women, 308. Men who agree when the interviewer is a woman. See, it just changes. 560 changes to 308. So if the interviewer is a woman, men who agree change to 308. And men who disagree change. So the point being, it does have an effect or it doesn't. Let's check it out. And that is the test of homogeneity that we are going to uh, look at here. So let's again quickly remind everybody of what we discussed. This is the synopsis of that. Chi-square test of homogeneity. Test of homogeneity of proportions is a test of the claim that different populations or groups have the same proportions or distribution of a single categorical variable. The test of homogeneity of proportion is used to determine whether the proportions for a variable are equal when several samples are selected from different populations. It tests if the proportion of categories are the same across different groups. Data structure, multiple samples, one variable, e.g. preference across age groups. Example, 3 age groups differ in their preference for the political candidate. Test of homogeneity, are right here. So all tests that are tests of independence, homogeneity, they are considered right. Now, we are dealing with a matrix here. Again, just as before, we have to create a matrix similar to that for the expected value. So what are we dealing with here? We are going to add these two. We're going to add these two, and that's the column. We're going to add these two. We're going to add these two, and the grand total. So again, please understand, add these two numbers, you get this one. Add these two numbers, you get this one. Now, the sum of these two as well as the sum of these two must be identical, and the answer is 1200. Otherwise, we've made a mistake. Now, we are going to use the same formula, row sum, column sum divided by grand total for the expected frequency. For example, for this one, I'm going to multiply these two numbers, 800 by 868, divide by 1200. Okay, so table of expected values is this. As an example, for 560, The expected value is the product of these two, 868 and 800, divided by 1200. And this number goes here as an expected value, 578.67. The rest of them in the same manner. Okay. So it's pretty straightforward. And of course, what about the requirements? Based on the description of the study, we will treat the subjects as being randomly selected and randomly assigned to the different posters. The results are expressed as frequency counts, numbers. The expected frequencies are all at least 5. It's way larger than 5. If so, the counts will be approximately normally distributed. And that's the idea, normal distribution. So we can use the chi-square distribution. All right, so we are going to continue working on that. First and foremost, test statistic, degrees of freedom R minus 1 times C minus 1. This is what we got from the previous page. And let's look at the table also. So starting with H0. Okay. The proportions of agree-disagree responses are the same for the subjects interviewed by men and subject interviewed by women. P sub 1 equals P sub 2 equals P sub 3 all the way to the end. Okay, in this case, there were 4 categories. Or you may say survey responses by men are independent of poster gender. You can use that wording, and that is the claim. On the other hand, H1, the proportions are different. The proportions of the same thing. At least one proportion is different from the others, or survey responses by men depend on poster gender. And again, we are taking it to be right tail test, and we are going to use the second step for test statistic, which means 560 minus 578.67. I'm looking at summation of O minus E quantity square over E. This one minus this one over this one squared. Plus the same thing all the way to the end. The last one would be plus 92 minus 110.67 quantity squared over 110.67. So these are, you have to write 1, 2, 3, 4 of them. Okay, I wrote the first one and the last one. You put it into a calculator, you end up with 6.529. Degrees of freedom. You have R minus 1. There are 2 rows, so 2 minus 1 times C minus 1. Columns, there are 2 columns, 2 minus 1 as well. So the degrees of freedom is 1. Alpha is 0.05. So on the table, you look for degrees of freedom of 1, alpha of 0.05, because it's a right tail test. And put together, you get this number. Therefore, chi-squared is 3.841. You do the drawing. It's always important to do the drawing. And when you do the drawing, chi-squared of 3.841 is your critical value. Test statistic is way into the rejection region. Therefore, reject H0. So reject H0, that means reject independence. That means if you're rejecting H0, you're rejecting the claim. That means the claim is false. And then you do the writing. There's not sufficient evidence to support the claim that the proportion of agree-disagree responses are the same for the subjects interviewed by men and the subjects interviewed by women. So that's one way to write it. The other one is that there is sufficient evidence to reject the claim of equal proportions. There's another way of writing. Survey responses by men depend on pollster gender. In this case, I wanted to write different methods because in case you come across them, you want to recognize all of them are the same. So there are 3 different ways of writing this. If we were to go with a 2-tail test, degrees of freedom of 1, we get those 2 values, okay? And obviously, this is larger than this number, and it gives you the same result. By the way, As far as technology, the p-value would be the area, this area to the right of 6.529, this area, just to the right of this one, which is clearly less than alpha. So again, you can use that method if with technology and so on. All right. Let's look at this one. Test of homogeneity using the following table with a 0.05 significance level. Alpha is 0.05. Test the association between people living in a city and becoming infected with a highly resistant bacteria. So we have people living in city and outside city. Okay. Bacterial condition infected, not infected. H0, whether a person is infected is independent of whether the person lives in the city or outside the city. In other words, P1 equals P2 equals P3 and so on. And that's the claim. And H1 is whether a person is infected is dependent of whether the person lives in the city or outside the city. And we make it right tail test. And so now we are going to use the test statistic, which says chi-squared is summation of observed value minus expected quantity squared over E. Degrees of freedom is R minus 1, C minus 1. By the way, you can clearly see that this, of course, has 2 rows and 2 columns just for the sake of this part. But as far as the test statistic, reminding you that we go with row sum, column sum divided by grand total, right? So if you add these two numbers, you get 10,162. You add these two numbers, you get 31,886. You add this column, you add these two numbers, you add these two numbers. The grand total must be the same across here and down here. And so, for example, again, just reminding you, for one of them, for this number, 4,239, I want to calculate the expected value. So I want to make sure that everybody can see how it's calculated. Okay, again, just to remind you of that. The row sum is this number, 10,162. The column sum is this number. So we're going to say, so this number times this number. The grand total is this number, 42,048. And we get that one. Now, we calculate the expected value for each cell. There are 4 of them, okay? So for one of them, 4,239, we got this number. And here's the rest of them when we do the calculation by hand or technology. Now, as far as technology is concerned, for example, Excel can calculate that and then use this formula and calculate it for each cell, which means, for example, for this one, 4,239 minus, I'm sorry, 4,200 minus 4,142.088 quantity squared divided by this number. And then you can write it for this cell and the next one and the next one and add them up. So I'm going to write this for this cell, as I said, 4,239 minus 4,142.08 quantity squared divided by 4,142.088 all the way to the last one. And you add up those numbers, and if you add them up, you get 5.047424. We are going, this is the test statistic. We're going to go with the critical value. Degrees of freedom is 2 minus 1, 2 minus 1, 1. Alpha is 0.05, again, because there are 2 rows and 2 columns. So chi-squared, just like before, is 3.841. And if you do the drawing, clearly you can see that the critical value is 3.841. and the test statistic was calculated to be 5.047, way into the rejection region. Okay. And by the way, so that means the decision is to reject H0. Let me just do this. By the way, this area to the right of test statistic is the p-value. So if you look at the technology, in this case, Excel, okay, it gives you the degrees of freedom of alpha, and this is the value that was calculated. Okay, let me just put that here, 5.04744, of course, with more decimals. Okay, sometimes critical value is again using more decimals than ours. The p-value is the area to this, to the right of 5.047, the test statistic, which is 0.02466, whatever. Clearly, in a matter of comparison to alpha, is less than alpha, and you get the same result. So the decision is to reject H0. When you reject H0, that means you're rejecting independence. So if you're rejecting H0, you're rejecting the claim. The claim is therefore false. Now you do the statement. There is not sufficient evidence to support the claim that whether a person is infected is independent of whether the person lives in the city or outside the city. In other words, whether a person is infected is dependent of whether the person lives in the city or outside the city. And as I mentioned, as far as the p-value is concerned, if you look at the p-value here, class, 0.02, and you can round this 4 next to this 6, so you change it to 5. Clearly less than alpha, and you have the same decision, reject H0. Same decision.